So in the last class, in our effort to prove the insolvability of the Quintic, we proved a result, and that result is this. Let F be a field of characteristic 0 and A belongs to F and K be the splitting field of x to the power of n minus a, then the Galois group of K over F is solvable. This is the result we proved in the last session. What we are trying to prove is that there exists a fifth degree polynomial in a field F with characteristic 0. The degree of this is 5, such that the splitting field of f of x is not an extension of f by radicals. This is our final goal. But before trying to find out a polynomial like this, we need to prove one more result. And that is, let F be a field of characteristic 0 and F is a subfield of E, which is a subfield of K, which is a subfield of F closure, where E is a finite normal extension and K is an extension of F by radicals, then the Galois group of E over F is solvable. So this means that the Galois group of every finite extension within an extension by radicals is solvable. Okay, so that is the meaning of this result. So let us try to prove this. And once we prove this, we need one more corollary. We'll go for that. See, so K is an extension of F by radicals implies there exists alpha 1 dash alpha r belongs to or in K and integers n1 dash nr such that such that alpha 1 to the power of n1 belongs to f, and alpha I n to the power of I belongs to f of alpha 1 dash dash alpha I minus 1. We'll take an example here, because we are going to construct a sequence of extensions of f by radicals. Okay, so our base field is q, f is equal to q, and E I'm going to consider as q of root 2 comma root of 1 plus root, and k is actually is equal to q of root 2 comma root of 1 plus root 2 comma root of 1 plus root of 1 plus root. See, this is also an extension by radical, but see, if k is an extension of extension of f by radicals, but if you take any subfield of k, it should be a finite extension of q, and it has to be one of these. So that is why I have to take either E is equal to this or E is equal to q of root 2. And both of them are actually extensions by radicals. Although we are considering this as a finite normal extension, it is really a extensions of f by radicals. We'll come to that here. Now what I'm going to do here is, I'm going to define a polynomial f1 of x, define f1 of x equal to x to the power of n1 minus alpha 1 to the power of n1. Where is alpha 1 to the power of n1? That is in f. So the coefficient of x are all in f. So this definitely belongs to f of x. So let us take the splitting field of this polynomial. So let L1 be the splitting field of f1 of x. Now, see, L1 is a splitting field of S, so L1 is the finite normal extension of F. And actually L1 is equal to f of alpha 1. And that implies L1 is an extension of f by radicals. And that implies L1 is a finite normal extension of f by radicals. Now we'll form so we can consider the Galois group. So the Galois group of G of L1 over F is solvable by the first theorem. Now we'll form another function, another polynomial, f2 of x. So in this case, our alpha 1 is equal to root 2, alpha 2 is equal to root of 1 plus root 2, alpha 3 is equal to root of 1 plus root of 1 plus root 2. And all n1, n2 and n3 are 2. So here f1 of x is equal to x square minus 2. And g of alpha, g of L1, so actually what is L1? L1 is equal to q of root 2. So g of L1 over f is equal to actually I comma sigma, where I is identity map and sigma is actually root 2 is equal to minus root 2. And this is solvable because that is an abelian group. Now we are forming another polynomial, that is pi of sigma varies over Galois group of L1 over f x to the power of n2 minus sigma of alpha 2 to the power of n2. See, what you are saying here is, I'm going to take x square minus alpha 2 is 1 plus root 2 times x square minus root of 1 plus 1 minus root 2. Because the sigma of root 2 is minus root 2, and that is what I am doing here. So this actually belongs to f of x. The reason for this one is because f2 is symmetric on the coefficients of x. They have symmetric coefficients here, because when sigma runs through this will become all the conjugates of alpha 2. So this is not actually changed by any induced sigma. That's what I'm trying to say here. So let us take the splitting field of this. So let L2 be the splitting field of f2 of x. So what will happen here? Again, this will imply L2 is a finite normal extension of f by radicals, and g of L2 over f is solvable. So I'm going to take this out. I just want to show how we are constructing the polynomials and its splitting field. So we continue this process until we get LR, and we'll call it as L, to be the extension of, so to be the splitting field of FR of X, which is pi sigma belongs to G of L R minus 1 over F XNR minus sigma alpha R. So what will happen here? You have K is less than or equal to LR, or LR is equal to M. So what we have here is F less than or equal to E less than or equal to K less than or equal to L less than or equal to F. Closure. This is actually the extension of F by radicals, and this is a finite normal extension of F by radicals, and this is actually a finite normal extension, which is definitely a finite normal extension by radical. Now, what else we have here? We also have G of L over F is solvable. So G over LF is solved. So here G of E over F is isomorphic to G of L over F over G of E over L over E. We know this, and that means G of E over F is a homomorphic image of, see, if you say H is isomorphic to G over, let's say not H, let's take another. If K is isomorphic to G over H, this means that for every G there is an element in K. The map is going to be like, let us take the map from here, from G over H to K by phi of A is equal to K plus A. So this is the homomorphism I'm talking about. So actually K is a homomorphic image of G. So E over F is a homomorphic image of G of L over F. But G of L over F is solvable. That means every homomorphic image of this is also solvable. So that means G of E over F being a homomorphic image is solvable. And that's what we want to prove. We are going to make use of a corollary of this theorem to find out the polynomial of degree 5 which is not solvable by radicals. So the corollary is like this. See, what does this mean? This means that here E is a finite normal extension of f by radicals. That means E is a splitting field of f by radicals over f, or splitting field over f by radicals. Right? So this theorem says that E is a splitting field over f by radicals implies G over E over f is solvable. What does this mean? This means that E is a splitting field of some polynomial in f by radicals implies G of f, the Galois group of E is solvable. Or in other words, if G over E over f is not solvable, if it is not solvable, then E cannot be a splitting field over f by radicals. And that is a corollary we are going to write. So we are going to write it as f is a f is an extension of, E is an extension of f, then G of E over f is not solvable implies E cannot be a splitting field over f by radicals. This is very important. Okay? If it is not solvable, it cannot be a splitting field over f by radicals. So this is what we are going to use. We are going to develop a polynomial such that its splitting field is not solvable. Then we are done. That means it cannot be an extension of f by radicals. So we are going to use the corollary to find out a polynomial of degree 5 whose splitting field is not an extension by radicals. So what we are going to assume is we are going to borrow a result from group theory again. Not going to prove this. This is very simple result. Actually, it is an exercise in group theory. It's not a theorem. What it says is the symmetric group S5 is not solvable. Symmetric group S5 means this is a group of permutation on 5 elements. This is not solvable. So our aim is to find a Galois group of a splitting field that is isomorphic to S5. If we can prove that there exists a splitting field such that its Galois group is isomorphic to S5, which is not solvable, what does that imply? That implies E cannot be a splitting field over F by radicals. Now, as I said before, F is of characteristic 0. But from the proof of this theorem, we are not going to take F is equal to Q. This is not we are going to take. We are going to take an extension of Q as a base, as F. So let us create that extension here. Before that, I want to recap one more definition from field theory, which I already done. Transcendental numbers. Transcendental numbers is an element A in Q is algebraic if there exists a polynomial in Q of X such that A is a 0 of that polynomial. Otherwise, it is a transcendental number. And there are uncountable number of transcendental numbers. Infinite number of transcendental numbers. So what we are going to do is we are going to form a polynomial. Okay, so let just a minute. Let y1 be a transcendental number. When you say transcendental number, that means it is transcendental over Q. Then then take y2 belongs to y2 is a real number. Y2 belongs to R such that y2 is transcendental over Q of y1. So choose y1, y2, y3, y4, y5 such that y1 is transcendental over Q and y2 is transcendental over over Q of y1, y3 is transcendental over Q of y1, y2, y4 is transcendental over Q of y1, y2, y3, and y5 is transcendental over Q of y1, y2, y3, and y4. So let us form the polynomial. Let f of x is equal to pi of x minus yi. I is from 1 to 5. And that means x minus y1 times x minus y2 times x minus y3 times x minus y4 times x minus y. So what are the zeros of this? y1, y2, y3, y4, y6 and y1, y2, y3, y4 and y5. So Q of y1, y2, y3 dash y4, y5 is the splitting field of f of x. So the coefficients of f of x are elementary symmetric functions. Elementary symmetric functions with a possible change in sign. What I mean by this is the coefficient of x is actually y1 plus y2 plus y3 plus y4 plus y5 with a negative sign. That's why I said the only difference in the coefficients are plus or minus elementary symmetric functions. Like that, S5 is, that is the coefficient of, or the constant term is y1, y2, y3, y4, y5. And coefficient of x square will be y1, y2, y2, y3, y3, y4, y4, y5, y1, y3, all combinations 2 at a time from 5 elements. So this means, therefore, f of x belongs to Q of S1, S2, S3, S4, S5. So this is our base extension. So our f is Q of S1, S2 dash S5, and our E is Q of y1, y2, y3, dash y5. Of course, f is a subfield of E. What we need to prove that the Galois group of E over F is isomorphic to S1. Once it is done, then we can say that this polynomial cannot be solved over Q of S1, S2, S3, S5, not Q, Q of S1, S2, S3, S5 by radicals. So what we are going to do here is we need to find out the automorphisms on this and see whether that matches with the automorphisms on the permutations here. So what we'll do is, for each permutation, sigma in S5 define a automorphism on G of E over F by sigma of A is equal to A for all A in Q, and when you come outside it will be a function of y1, yi's. So sigma of, we'll write it as sigma bar because this is an automorphism and this is a permutation. For each permutation we are defining an automorphism in here. So sigma bar of yi is equal to y of sigma I. This is actually the permutation of I, where the I is mapped to. So this is perfectly an automorphism on here. So for every permutation on S5, there is a unique automorphism on the Galois group. And that means the order of the Galois group is less than or equal to order of S5, and that is equal to 5 factorial. Now what we are going to do here is, E is the splitting field of this has to be greater than, this has to be greater than, because for every automorphism here, for every permutation here, there is an automorphism here. So it should be actually greater than this. So E is a splitting field of f of x, which is a degree of 5. And that means the elements of this, the number of elements of this cannot be more than 5 factorial. And that implies G of E over F is isomorphic to S5. Basically what means is for every, or you can say this map is a bijective map, meaning for every permutation sigma on S5, there is a automorphism on G of E over F, and for every automorphism sigma bar on G of E over F, there is a permutation on S1. So that means we are almost done. That means the Galois group is not solvable. That means G of Q of y1 comma y2 comma dash dash y5 over Q of s1 comma s2 dash dash s5 is not solvable. And that means the splitting field of f of x is not an extension of Q of S1 dash dash S5 by radicals. It is an extension, but it is not an extension by